In 1957, at a small observatory in the hills west of Puebla, Mexico, a telescope photographed a patch of sky in the constellation of Canes Venatici. The plates came back showing what appeared to be a faint blue star. Unremarkable, distant, barely visible. A cataloging note was made. The object was logged, and then it was filed away. It was not a star. It was not even close to a star. What the Tonantzintla Observatory had accidentally captured was the most luminous object ever discovered in the observable universe. A quasar so energetic that it outshines every star in the Milky Way combined, multiplied by over 1,000. And at its center, doing the impossible, sits a black hole so massive that physics says it should not exist. 66 billion times the mass of our sun. An event horizon, the boundary of no return, so wide that it would swallow our entire solar system past Pluto and keep going, 40 times over. We call it TON 618. And the deeper you look at what it is, how it formed and what it means, the more clearly you can see a single, disturbing truth emerging from the mathematics. The universe built something it was not supposed to be able to build. Before we can understand what makes TON 618 extraordinary, we need to understand what black holes are allowed to do. Most people have a rough picture. A massive star collapses. Gravity overwhelms every other force in the universe. Matter compresses into a singularity, a point of infinite density, wrapped in an event horizon, the surface beyond which even light cannot escape. The more matter falls in, the more massive the black hole becomes. Simple enough, and for most black holes, the stellar mass ones scattered throughout galaxies, weighing between a few and a few dozen solar masses. That picture is basically right. But supermassive black holes, the giants sitting at the centers of galaxies, work differently. They feed, they accrete. Matter swirls around them in a superheated disk, spiraling inward, compressed and heated to millions of degrees, radiating enormous energy before crossing the event horizon and vanishing from the universe forever. That radiation is the key, because it creates a problem. As a black hole feeds, as matter falls inward and heats up, the energy it releases pushes outward, not just light, not just heat. Radiation pressure, a physical force pushing back against the very gas trying to fall in. The faster a black hole feeds, the more radiation it produces. The more radiation it produces, the harder it becomes for additional matter to approach. At a certain feeding rate, a certain luminosity, the outward radiation pressure exactly balances the inward pull of gravity. The flow stalls. The black hole, in a very real sense, chokes on its own light. This balance point has a name, the Eddington limit. And it is not just a guideline, it is a hard physical constraint arising directly from the equations of radiation pressure and gravity. Exceed it and the black hole's own accretion disk blows itself apart. Every supermassive black hole in the universe grows under this constraint. Every one. The Eddington limit sets an absolute ceiling on the rate of growth, and by extension, on how massive a black hole can become in a given amount of time. The universe is 13.8 billion years old. The Eddington limit tells you how fast a black hole can eat. Multiply one by the other and you get a number. Approximately 50 billion solar masses. That is the theoretical maximum mass for any black hole that grows by normal accretion. By feeding on matter in the conventional way, limited by the Eddington constraint over the entire age of the universe. TON 618's black hole has been measured at 66 billion solar masses. The universe apparently did not read the textbook. Let us talk about the scale for a moment, because the numbers alone do not tell the story. Numbers need translation before they become real. The black hole at the center of our own Milky Way galaxy is called Sagittarius, a star. It has a mass of approximately 4.15 million solar masses, 4 million times the mass of our Sun. It is one of the largest objects most humans will ever learn about in the course of a lifetime of astronomy education. TON 618's black hole is 15,300 times more massive than that. The combined mass of every single star in the Milky Way, every red dwarf, every giant, every white dwarf, every neutron star, adds up to approximately 64 billion solar masses. TON 618's black hole, sitting alone in the center of a galaxy we cannot even see clearly, and is more massive than all of them together. Its event horizon, the Schwarzschild radius, the boundary of no return, spans 1,300 astronomical units in radius. 1 astronomical unit is the distance from Earth to the Sun. So the event horizon of TON 618 extends outward 1,300 times the distance between our planet and our star. In diameter, it stretches roughly the equivalent of placing our entire solar system end to end more than 40 times. If you replace the Sun with TON 618 tomorrow, which is not how any of this works, but follow the image, its event horizon would not merely swallow Earth or Mars or Jupiter. It would engulf Neptune, Pluto, and continue past the Kuiper Belt and well into the outer solar system before it finally stopped. And that boundary, that enormous silent sphere of absolute finality, is not the black hole itself. It is just the edge of where physics as we understand it surrenders. But here is the deeper problem. The size alone is not what breaks the model. The growth rate is. The light we receive from TON 618 has been traveling for approximately 10.4 billion years. We are not seeing what TON 618 looks like today. We are seeing it as it existed when the universe was roughly 3.3 billion years old, less than a quarter of its current age. That means this black hole with its 66 billion solar masses already existed at that mass when the cosmos was barely a toddler. Think about what that requires. If we accept the Eddington limit as a hard ceiling on accretion rates, and we accept that black holes begin as stellar remnants, the collapsed cores of massive stars typically weighing a few tens of solar masses, then growing to 66 billion solar masses in under 3.3 billion years is, under standard models, essentially impossible. You would need to be accreting at or near the Eddington limit continuously every moment with virtually no interruption from the earliest moments of the universe. No known black hole does that. Growth is episodic. Mergers happen, but they take time. Gas supplies are not infinite or constant. And even at the Eddington limit, the math struggles to account for the mass we observe. Current models suggest that to explain TON 618's existence, at least one of 3 things must have happened, possibly all 3 simultaneously. First, the black hole's seed may have been born large, not from a stellar collapse which produces a black hole of tens to hundreds of solar masses, but from the direct collapse of a massive gas cloud in the primordial universe. A process called direct collapse, bypassing the stellar stage entirely and producing an initial seed of perhaps 100,000 to 1,000,000 solar masses. Theorists had proposed this pathway before TON 618 drew attention to it. Objects like TON 618 are now the best observational motivation for taking it seriously. Second, the growth almost certainly involved episodes of super Eddington accretion, feeding at rates that exceed the theoretical limit by factors of 10, 20, perhaps 100. This is not physically impossible in extreme environments. When the surrounding gas density is high enough, and the geometry of infall channels matter efficiently toward the singularity, radiation can be trapped inside the infalling gas rather than pushing it away. The black hole eats faster than it should be allowed to. Current models suggest this must have been sustained, not occasional, over billions of years. Third, mergers. The early universe was a dense, violent place. galaxies colliding and consuming one another at rates far higher than today. Each merger can bring two black holes together, and two black holes merging do not just add their masses. They release gravitational waves, ripples in space-time itself, and the recoil can reshape the orbit of the merged product within its galaxy, funneling more gas toward it. Merger after merger, feeding period after feeding period over the first 3 billion years of the universe's existence. And this is where it gets dangerous. Even combining all three mechanisms, a massive direct collapse seed, sustained super Eddington accretion, and repeated galactic mergers, current cosmological simulations still struggle to produce objects as massive as TON 618 by the redshift at which we observe it. They can produce very large black holes. They cannot comfortably produce this one, this early, this consistently. TON 618 is not just a record, it is a falsification test. And the standard model of black hole growth has not yet passed it cleanly. Stand in your imagination at a distance of 10 light-years from TON 618, close enough for the physics to become visceral, far enough that you are not yet inside anything you cannot leave. What you see from here is not a black hole, not in any visual sense. What you see is a blaze, a wall of light so intense that the word bright becomes inadequate. The accretion disk surrounding TON 618 radiates with the luminosity of 140 trillion suns. Not 140 trillion individual stars scattered across a galaxy. 140 trillion suns concentrated, blazing from a region smaller in relative scale than a period at the end of this sentence. The light is not white. It is violet blue at its hottest, where the innermost disk material reaches temperatures measured in hundreds of thousands of degrees. But the disk is so thick, so turbulent, so layered with radiating gas and magnetic field lines twisted by orbital shear, that its full spectrum spans from X-ray to radio, every wavelength at once. A total electromagnetic scream that no instrument we have yet built could measure without being destroyed. Around the quasar, extending outward for hundreds of thousands of light-years in every direction, a vast nebula of gas, called a Lyman alpha blob, glows blue-white in the ultraviolet, ionized by the quasar's radiation. Its diameter is at least 330,000 light-years. That is triple the diameter of the Milky Way. The Milky Way would fit inside this glowing cloud 3 times over. And at the center of all of it, invisible by definition, is the black hole itself, an event horizon 1,300 astronomical units in radius, sitting in the precise spot where 66 billion solar masses of matter have compressed into a gravitational singularity that curves space-time so severely that physics as we write it stops being a reliable guide to what happens next. The tidal forces at the event horizon of TON 618 are, by contrast, relatively gentle. A strange and counterintuitive fact about very massive black holes. The larger the black hole, the weaker the tidal gradient at its surface. A stellar mass black hole would shred you into a stream of atoms before you reached its event horizon. TON 618 would pull you across with barely a gradient you could feel. You would cross the boundary without knowing it. The moment after would be different. Inside the event horizon, space-time geometry dictates that every path, every possible future, leads toward the singularity, not just the path you choose. All paths, in every direction. You cannot avoid it any more than you can avoid moving forward in time. The singularity is not a place, it is a when. How long it takes to reach it from the moment you cross the event horizon depends on the geometry. But for a black hole, this massive estimate suggests it could be hours or even days of subjective experience before the end. Silence. Then nothing. And then nothing, in the most complete sense that word can mean. The first time anyone wrote down the number 66 billion solar masses with confidence, was in a 2004 paper by researchers who analyzed the broad emission lines in TON 618 spectrum. The H-beta line in particular measuring the velocity of gas orbiting near the black hole using a technique called reverberation mapping. The gas was moving at an infalling speed with hints of 10,500 kilometers per second, about 3.5% of the speed of light. From that velocity and the estimated orbital radius, the mass follows directly from Newtonian gravity and its relativistic corrections. The result was immediately uncomfortable, because around the same time the theoretical framework for black hole size limits was being sharpened. In 2015, Professor Andrew King at the University of Leicester published a paper examining what happens at the innermost stable circular orbit, the ISCO, around a growing black hole. The ISCO is the innermost edge of the accretion disk, the closest stable orbit from which matter can spiral inward. As a black hole grows more massive, the ISCO moves outward. The problem King identified is that at very high masses, the ISCO is pushed beyond what's called the self-gravitational radius, the distance at which the gravitational pull of the black hole on disk material is overwhelmed by the mutual gravity of the disk material on itself. At that point, the disk cannot hold together. Material in the disk can no longer lose enough energy through collisions to reduce its orbit and fall in. The black hole has, in a physical sense, grown beyond its own feeding mechanism. King's calculation placed this limit at approximately 50 billion solar masses for a non-spinning black hole, and up to 270 billion solar masses for a maximally spinning one. TON 618 at 66 billion solar masses sits above the non-spinning limit. The implication is either that it is spinning, which is entirely plausible and unverified, or that something about our model of how accretion works at extreme masses is incomplete. Here is the part most people miss. This means that TON 618 may not be able to grow much larger. It may be approaching, or already at, the point where it simply cannot feed anymore, where the physics of accretion breaks down around it, where the black hole for the first time in its existence has run out of things to eat. And that brings us to the strangest question of all. What is TON 618 doing right now? The answer is we have no idea, and we cannot know. The light we are observing from TON 618 left that object 10.4 billion years ago. What has happened in the intervening 10.4 billion years? Whether it is still an active quasar, whether it has grown further, whether it has gone dark, is completely beyond our observational reach. The universe is expanding. The light from TON 618 today will never reach us. Whatever state it is in at this moment is, in the most fundamental physical sense, unknowable to us. But we can reason about it. Quasars do not last forever. They are powered by active feeding, by the continuous infall of gas and matter from a surrounding disk. As the local gas supply depletes, the feeding rate drops. The luminosity fades. The quasar dims. The disk disperses. And what is left is a massive, silent black hole sitting at the center of a galaxy, no longer blazing, no longer visible at cosmological distances. A dead quasar. Astronomers believe that many, perhaps most, of the massive dead black holes sitting at the centers of local galaxies, including the galaxy just a few megaparsecs from the Milky Way, are the remnants of quasar phase activity in the early universe. The bright, violent objects we see at high redshift become the quiet monsters embedded in mature galaxies closer to us. What does the dead remnant of TON 618 look like? Potentially the most massive object of its kind in the local universe. A black hole of perhaps 66 billion or more solar masses, sitting at the center of a galaxy we cannot identify, surrounded by stars that have long since stopped feeding it, in a state of silence that could persist for trillions of years. Scientists now believe it may fall into a category that did not formally exist before objects like TON 618 forced its creation. Not supermassive, something beyond that. Ultramassive. Black holes with masses exceeding roughly 10 billion solar masses, where the standard scaling relationships between galaxy mass and black hole mass break down, where the physics of accretion may operate differently and where our models are openly, demonstrably incomplete. The word ultramassive is not yet universally adopted in the literature. It appears in some studies as absent from others and remains a proposal rather than a settled classification. The fact that we are still arguing about what to call it says everything about how far beyond our frameworks this object sits. The implications for cosmology are not abstract. Every model of galaxy formation depends on feedback, on the idea that the black hole at the center of a galaxy regulates its own growth and the growth of the surrounding stars. As the black hole feeds, its radiation heats and expels the surrounding gas, slowing star formation, eventually starving the accretion disk and putting the brakes on both the galaxy and the black hole simultaneously. This feedback mechanism is foundational. It explains why the mass of a galaxy and the mass of its central black hole track each other so consistently across the observable universe. It is one of the most robust relationships in extragalactic astronomy. TON 618 challenges that picture in a specific and productive way. If the black hole grew to 66 billion solar masses in under 3.3 billion years, faster than the Eddington limit strictly allows, and to a mass above the theoretical accretion ceiling, then either the feedback mechanism failed to operate normally, or the gas supply was so extraordinarily abundant that it overwhelmed the feedback, or the growth involved a merger history so extreme that the standard relationship never had time to establish itself. Any of those scenarios tells us something important about conditions in the early universe that our current models do not fully capture. And the fact that TON 618 is not alone, that surveys have now found multiple objects with comparable masses at high redshifts, tells us this is not a fluke, not a measurement error, not a single anomalous data point. It is a pattern, and patterns in conflict with models are how physics invents.